So welcome and thanks for joining us today, both in person and at Monash, in person here at Monash University and online via Zoom. I'm Professor Joanna Batstone and I'm the director of the Monash Data Futures Institute, and I'm your host and moderator for today. Before we start, I wish to acknowledge the people of the Kulin Nations on whose land we are gathered today, and I pay my respects to their elders past and present. Welcome to another one of our Monash conversations on AI and data science. We've had a great series of talks through this year, and we're really delighted to see a great audience again today. And this series of talks is designed to enable us to highlight some of the impactful data science and AI research that we have going on across Monash University, and to share that work with our Monash community, but also with those of you who are joining us today, perhaps for the first time, as external guests of this seminar series. So thank you for joining us. We're very pleased to have you here. Today, we're pleased to host Associate Professor Jianning Song from the Faculty of Medicine, Nursing and Health Sciences here at Monash University. Jianning is the group leader in the Cancer and Infection and Immunity programs at the Biomedicine Discovery Institute. He's got many other awards and honors. He's also an associate investigator of the ARC Center of Excellence in Advanced Molecular Imaging. And he's the founding member of the Monash University Center to Impact on Antimicrobial Resistance. His lab is interested in tackling biomedical problems with large amounts of data generated by high-throughput techniques that span 2 strategic research programs involving cancer and infection and immunity programs. Jianning is also a member of the Monash Data Futures Institute as a member of our affiliation program, and he's been very actively engaged with us over the last 3 years in a number of different research projects. Today, we're delighted to give Jianning the opportunity to present some of the research work he's been involved in that is funded and supported by one of our Monash Data Futures Institute seed grants. And so today, we're going to hear about his work on AI approaches for cancer diagnosis, type classification, and mutation prediction. It's great to have you with us again, Jianning, today. Over to you. We look forward to your talk.
Thank you so much, Joanna. Good afternoon, everyone. It's my great pleasure to have this opportunity to share with you some of my team's recent research works on the frontier of computational pathology or computational oncology. I changed the presentation title a little bit. I tried to introduce some of the work that we developed regarding the AI approaches for several different downstream analysis tasks regarding digital pathology. So I suppose the tools that we developed can be used to address, for example, cancer diagnosis, also subtypes of subtypes of cancer, and also some of the oncology mutation, as well as prognosis analysis, like predicting the cancer patient survival for different types of cancer patients. So there will be 2 major types of image data involved. The first type is the whole slide histopathological images, which is routinely used clinically by pathology to assess stage, progression, or type of solid tumor. And the second emerging type of image is called multiplexed histofluorescence or immunohistofluorescence or immunohistochemistry, mIHC images. So this type of images, they are commonly generated by antibody staining. So nowadays, the commercially available technique can enable the staining of, I suppose, around 1,000 different molecular biomarkers. So we are going to introduce some of the AI approaches surrounding the handling, processing, modeling, analysis of these 2 primary types of image data. With this slide, I just want to briefly share with you my research group's primary interest. So we are currently experiencing a profound paradigm-shifting trend in modern contemporary biomedicine. So in this process, we are interested in designing, developing, deploying data-driven algorithms, tools, softwares, toolkits, resources, databases to address a range of open but perhaps challenging questions in the 4 disciplines, including structural biology, genomics, microbiology, and also cancer biology. So the core in this program is regarding the development of data-driven computational algorithm and also the user-friendly software that can better cater for different downstream users' needs. I would like to showcase 3 different research works. The first one will be focused on whole slide image analysis. As we know, the visual inspection examination of cancer histopathological slides remain to be one of the predominant primary approach to assess stage, type, and subtype of solid tumor. Specifically, in the case of lung cancer, there are 2 subtypes respectively called adenocarcinoma or squamous cell carcinoma. These 2 different subtypes of lung cancer, in a work published in Nature Medicine a while back ago by a research group from New York University School of Medicine, they reported the development, I suppose, the very first deep learning approach that take into consideration the whole slide image tiles into the deep learning model. And they show that deep learning model can be used in a fully automated manner with a predictive performance comparable to those of human expert pathologists for classifying the 2 different types of lung cancer, lewd and leuk, from the normal lung tissue. So the performance really was comparable to some of the well-trained human pathologists. And we are very intrigued, very inspired by those works. So that motivated our team to further deploy some of the deep learning-based frameworks to address a number of different questions. And we have published quite a number of papers in this domain. First, we introduced the HEAL software pipeline. So HEAL, the full name is called hematocylin and eosin image analysis pipeline. So we intend to develop and deliver this software package in a easy to deploy, flexible to configure, end-to-end version. So this can best facilitate interest users their efforts in terms of training their own deep learning model using their own curated histopathological image datasets. There are 2 different input to the HEAL pipeline. The first input is just the digitalized whole slide images. So normally the magnification level should be around at least 20 or even 40 times. And the second type of label would be really depending on the downstream analysis task. For example, if it's just a cancer diagnosis, we are interested in identifying the cancerous region. So for the cancerous region, the label would be 1. Then non-cancerous normal tissue region would be 0, for example. So that's the label for the samples. If it is like regarding the cancer subtyping task, for example, in the case of lung cancer, we have 3 different types, lewd, leuk, and also the normal lung tissue. So 3 different label classes. For other type of cancer, it will be, there may exist more than 4, even 6 different molecular subtypes, for example. And also depends on whether we are interested in predicting the mutation. Well, in most cases, it will be a binary classification task. So once user can define and be supplied with the 2 different types of input, they can configure the HEAL software package and configure the whole software and to train the deep learning model. And within the HEAL software package, there are up to 16 different deep learning architecture included. So there are some of the example outputs that can be generated by using the HEAL package. For example, some of the data distribution in terms of patient level or the smaller patches level or tile level image distribution, and also like generation plotting the ROC curve to better assess the performance of deep learning model, and also indeed to monitor the model training, the model training. During the model training process, we can generate some of the curves to better monitor the ACC and also the loss curve. Then we can better decide if the deep learning model already converts. Hence, we can stop the model training. And also some of the confusion metrics. These are the typical outputs that can be generated to evaluate the model of deep learning. And also, the outputs also can include like some of the digital generated heat maps that can be used to assess indicates, for example, highlights, identify some of the region in interest that commonly correspond to the cancerous region. And also, we also couple with other third-party software in order to better enhance the interpretability of deep learning model, such as using the GradCam algorithm to highlight those of the highly attentive regions that can correspond to regions that make an important contribution to the model prediction output. So basically, here is a software that can better facilitate users' efforts in cases where users have their own histopathological image dataset with proper labels of the sample. Then user may have the need to deliver their own deep learning model. I just want to highlight some of the different case studies. The first case study that can be performed using here is a multi-class classification task. In this task, we are interested in performing the subtyping of the lung cancer. There are 3 different subtypes of lung cancer: lewd, leuke, and normal lung tissue. So we just apply the ResNet deep learning architecture included in the HEAL software package and perform single round of deep learning model training. So these 2 approaches basically provide a distribution of the patient level and also the tile level image distributions. And we can see that at the whole slide image level, the number of the images are relatively smaller. However, after we partitioning the whole slide image into smaller patches using a sliding window approach, we can generate a much larger training dataset size. The deep learning model would be trained using at the tile level. And we can see that at the tile level, there will be more than close to even more than 200,000 tile images generated. So deep learning model would be trained at the tile level. Then the final prediction outcome will be generated after aggregating the prediction outcome at the tile level. These are the typical ROC curves that are used to assess the model performance. As we can see here, for the 3 subtypes of lung cancer, the AUC value, the area under the ROC curve, is very close to 1.0. That indicates that for identifying the normal lung tissue from histopathological images, the model is very accurate. While in terms of the 2 other subtypes of lung cancer, in the case of leuke, the model could achieve a AUC value of 0.89, while in the case of lewd subtype, the model can achieve an AUC value of is close to 0.87. While at the patient level, the accuracy can be further enhanced. The AUC value for the 3 different subtypes are all higher than 0.9. This indicates that indeed we could leverage HEAL software to train deep learning model for discriminating or classifying the 3 different subtypes of lung cancer. The second case study utilizing the HEAL package is a multi-label, multi-class classification task. Here in this task, we are more interested in addressing the question of whether or not we would be able to identify the oncogene mutation directly from the histopathological images. Therefore, in order to address this question, we trained 10 different classification models. According to the Cancer Genome Atlas database distribution, there are 10 most frequently genes in terms of lung cancer. So including TP53, which is a very famous tumor suppressor gene, and also a bunch of other kinase genes involved. And for each of the individual oncogene, we trained a corresponding deep learning model. So these ROC curves indicate that, out of the 10 oncogenes, at least 7 of them would be reasonably well predicted directly, their mutation status would be directly predicted from the whole slide images. So this indicates that indeed would be possible for us to perform image-based gene biomarker discovery. So this not just apply to the lung cancer patients. I think in a very recent study published in Cancer Cell by a group from Germany, they show that they can also train a more advanced transformer-based deep learning model for predicting some of the very well-known oncogene for the colorectal cancer. So that's another type of cancer. And we are also analyzed other cancer type here. So for the colon cancer, there are two predominant subtypes of colon cancer. One is called MSI, the other is called MSS. So MSI is a microsatellite instability subtype versus microsatellite stability subtype. And we also performed this case study and trained the model. So the results indicated that even for the two subtypes of colon cancer, deep learning model would have the capacity to predict their subtypes directly from the whole slide images. Although the AUC value for these two subtype of colon cancer was a little bit lower, less than 0.65. I guess one thing is that we used a very smaller publicly available data set from TCG. If we could have access to a much larger patient cohorts, we would be able to further improve the model performance. Then I would like to also introduce the second work. The second work is about predicting 4 different molecular subtypes of gastric cancer. So from the perspective of protein genomic characterization of gastric cancer patients, so whole exome sequencing analysis indicates that for gastric cancer, there are basically 4 major molecular subtypes. So those 4 molecular subtypes can only be determined after sequencing. So we want to know whether or not, again, it would be possible to train a deep learning model directly from histopathological images and apply the model to predict these 4 different molecular subtypes of gastric cancer. So our approach should be the first one worldwide for predicting the molecular subtype of gastric cancer. So in order to do this, we developed a deep learning ensemble-based computational framework. So there, again, we could only have the access to the TCG public patient cohort. So the TCG patient cohort only provide 332 whole slide images that represents 295 individual patients. So we could only start with this relatively smaller data set, and we train our model. Because deep learning model are very inclined to be overfitted. Therefore, we introduced the ensemble training strategy by training 10 different child models, then further aggregate the performance, the prediction results of these child models in an ensemble manner. So in this way, we could be able to, on one hand, reduce the risk of having overfitting, and second, and maintain a relatively generalizable, stable model performance. So for the 4 molecular subtype of gastric cancer, they include the EBV virus causing a gastric cancer subtype, the microsatellite instability, chromosome instability, and also genomically stable subtype. These performance tables just to give us an idea about the model comparison between models trained using ensemble strategy and also those counterpart model trained without ensemble. As we can see here, in general, I mean, for the for the 4 molecular subtypes, most of them, after we apply the ensemble training strategy, the performance for the molecular subtype would be enhanced. So therefore, this strategy have several advantages. First advantage that for deep learning model construction using a relatively small scale benchmark dataset, this strategy can reduce the possibility of having model overfitting. The second advantage that this method provides an approach for simultaneously predicting 4 different molecular subtypes directly from whole slide images. And the ensemble learning strategy also ensure and enhance a stable model performance. We should further evaluate the performance of the model. In addition to the 5-fold cross-validation, we also perform independent tests. Again, because the dataset was only retrieved using TCG public database, so we only had a relatively smaller independent test dataset. Again, we can see that at least for 3 molecular subtypes, the deterioration of the model assessed using the independent test dataset was much smaller, except 1 molecular subtype. So this indicates that it's possible to develop deep learning model from histopathological images to identify, predict molecular subtype of gastric cancer without the need of sequencing. So after we construct the deep learning model, we could readily apply the model to perform in silico digitalization of the images. I mean, depending on the particular downstream task, the digitalized map can be generated after applying the deep learning model. So this would be very useful in terms of shedding light on some of the region of interest that are considered by the model to be pertinent to the performance or to the outcome prediction of different subtypes of cancer. The third research I would like to share is that we move on to a relatively new medical image data, mIHC images. So characterization or quantification delineation of the tumor microenvironment is an ongoing challenge. So using the OPAL multiplex immunohistochemistry or immunofluorescence imaging method, multiple markers can be simultaneously stained on a single cancer tissue. So this can bring a very rich information regarding the tumor microenvironment. So a rationale or a hypothesis that we had at that time is that if we can develop like a graph-based deep learning approach that can better model the spatial local organization of the different cell types or different type of cells that are stained, identified using different type of molecular biomarkers, then perhaps we will be in a much better position to extract the rich information from the tumor microenvironment, which might be more informative or indicative of a potential the treatment outcome or survival status of the patient, or even predict, for example, the duration of the patient's survival. So that's why we developed the cell graph-based approach. This approach is different from the traditional convolutional neural network deep learning approach. It's based on the graph neural network. So we developed this approach and apply this approach to predict the gastric cancer patients, the prognosis prediction of gastric cancer patients directly from the multiplex mIHC image data. So our approach can be used to perform two different prediction tasks. One is called binary prediction. Here, binary prediction, I mean the patient survival is categorized into short-term survival versus long-term survival. It's called binary class, short-term survival versus long-term survival. And then the triple class or ternary class prediction, I mean, so the patient survival is classified into three different classes: short-term survival, intermediate survival, and also long-term survival. And we further made a comparative analysis between our approach, the patient stratified by our approach, and compared with those stratified using the conventional TM staging system. And we show that our approach can provide comparative or even competitive better statistical significance in terms of stratifying different patients. So the patient cohort we utilize actually were obtained from Ruijin Hospital, Shanghai Jiao Tong University School of Medicine. So we collaborated with Professor Da Kangxu's group from Ruijin Hospital. So in terms of the patient cohort distribution is shown in this table. I just want to briefly mention that there are, for the binary classification of patient survival, there are two different survival lengths. One is less than 24 months or equal to 24 months. The other is like longer than 48 months. That's binary class. While in the case of triple class or ternary class survival, patients are classified into with survival length less than 12 months, between 12 months and 16 months, and also longer than 16 months. This is just the methodology workflow for our approach. There are several stages involved in the development of cell graph signature approach. So basically, patient tissues were extracted, then followed by mIHC staining. We utilize 7 different biomarkers to stain the patient tissue samples. Then after that, we pre-process the images, especially in terms of representing the images as like cell-cell interaction graph, cell-cell communication graph. Then after representing the tumor microenvironment as different type of cells or different cells that stand by different colors in terms of network, communication network, we will be able to model their potential relationship using graph-based deep learning method. So for graph neural network, there are 4 major architecture, including GCN, SAG, GCN top K, GCN, GISAG, and GIN top K. We performed benchmarking analysis and show that among the 4 alternative deep graph neural network architecture, GIN top K provide the best performance. Then we train the model, optimize model, apply the model to predict the gastric cancer patient survival in terms of 2 class, binary class, and also ternary class. This just shows that the GIN top K provides overall best performance compared with the other 3 alternative GN architecture. These are the ROC curve again, generated on the independent test cohort of the patients. And we can see that the AUC value is pretty high. This indicates that the tumor microenvironment information is tried to represented using the cell graph network, then further modeled by graph neural network model can indeed is very informative for predicting the prognosis, the patient survival. So we further compared the stratification performance between our approach and the existing currently available TM staging approach, and compare the binary class, the patient with short-term survival and long-term survival, also the ternary class, short-term survival, intermediate survival, and long-term survival. And we generated the Kaplan-Meier curve shown in this figure here. And this is for the binary class patient survival prediction. As we can see here, although our cell graph-based approach was worse than the TM6 method, but still performed better than TM2 method. Again, further, after integrating our model's prediction results together with the TM2 stage, we could further enhance the C index, improve the C index to 0.748, and also with a statistical significance p-value, which was less than 0.001. This indicates that our approach can provide somehow complementary information compared with the traditional TM approach. This is for the binary patient survival stratification. While the model performance was even more pronounced when we applied model to predict the triple class patient survival. As we can see from these KM curves, we can see that our approach cell graph led to the best C-index value, which were much more significantly better than either the TM3 or TM6 approach. So this indicates that our approach at least can be used as a assistive tool to assess, to predict the gastric cancer prognosis of the patients. I think that's all the results I would like to share. Finally, I would like to thank my collaborator, including Professor Roger Daly, Professor Jeff Webb, Professor Chris Bain, also Terry Kwok, and Yan Nan, and Zhi Kang. My international collaborator, local collaborator also include Professor Alex Bosiutas and Professor John Zachber from the Alfred Health. Also international collaborator from Shanghai Jiao Tong University, Professor Da Kang-Xu Group. Also Professor Seiya Imoto from the Institute of Medical Science, University of Tokyo. Also Professor Pietro Liu. So he's a chief investigator, group leader in the Cambridge AI Center for Medicine. And also Professor Aris Sirigos and also Nicholas Kodry from New York University. So I also would like to acknowledge the funding support coming from the MRFF and HMRC, University of Tokyo, and also ARC. In particular, also the Monash RDR grant, which would not be possible for us to perform this type of work without those interdisciplinary research support. Thank you very much.
Thank you very much, Jianning. A great presentation, lots of information there, and my head is still spinning trying to understand this amazing amount of work that you've been doing. So thank you very much. We're going to move now to the question and answer session. For those of you on Zoom, please drop questions you may have into the chat, and we'll alternate them back and forth with the questions from the room. But let me ask first, if there are any questions from anyone here in the room? Okay, I've got a few.
Yeah.
But let me kick off with my first one. If I understood it correctly, your first set of analysis, you had work looking at lung cancer, and then you had some work you showed looking at the gastric cancers, I believe.
Yes. Yeah.
In the first lung cancer analysis, I think you pointed out that the analysis of the tile-based approach gave you better accuracy compared to patient, but it looked like when you got to the gastric examples, it was completely reversed. And so you had the tile-based approach was giving lower accuracy than the patient-based approach. And so I was just curious as to why one approach is better than the other when you're looking at two different types of cancers with a similar methodology.
I suppose there are multiple confounding factors that may influence the ultimate performance of the model. So one thing is we are still very limited in terms of the annotation quality of those whole slide images. So these are very important actually. And some of the very recently developed methods, they are already utilizing millions of those images already, to be honest. While the work we performed, actually, we could only access to a few hundred whole slide images. This is really put us in a very inferior position to really ensure the model performance generalization of the model. Another thing is different downstream tasks, the performance may be quite different. So for the cancer diagnosis, the performance would be, I suppose it's a solved, addressed question in terms, identifying the cancerous region boundaries from the images. That's a resolved task. But for molecular subtypes, whether or not some specific molecular type can be correctly predicted directly from images can be still challenging. Some of the molecular subtype, for example, like microsatellite instability, there have been some ongoing studies even now to date. So researchers are trying to integrate multiple different cohorts to really train a weakly supervised model to boost the predictive power for this single microsatellite instability, because it may have a lot of important clinical relevance application if we can correctly predict them directly from the images without sequencing the patient's genome. So that's one thing. Another thing is that, for example, even for the treatment response, there have been some other studies. We didn't even touch the treatment response. We don't have the label, to be honest, but we are collaborating with other hospitals now to collect the patient data. For example, one recent work, which is already funded by Cabrini Hospital, it's a private hospital here in Melbourne. They provide like more than 7,000 patient data, whole slide images, together with some tissue microarray data with the relapse, like treatment response. So I think we will be able to even develop more accurate AI model predicting the patient response. So that will be able to identify patients that can better respond to a specific treatment option. I also identify patients that may have higher risk. So these different downstream tasks, the performance may be very, very different.
Yeah, but I think what you're saying is because you've got such a small data set of images to start with, it's actually not significant whether you're choosing a tile approach or a patient approach when you're looking at that analysis.
Yeah.
Okay, okay. Got some questions in the room now. We've got our roving microphone walking around. Thank you.
Thanks, Jianning. So great work. And I'm wondering, how is the results of this work also going into communication with patients and families when you talk about prognosis? So obviously here we're going to get a bit better predictions on prognosis, perhaps with certain types of cancers. Is that going to be something helpful for maybe patients and families understanding the course of their disease?
The data regarding the patient survival, these are the retrospectively collected data. So we didn't have any efforts regarding prospectively collecting the data regarding the patient survival. So a lot of patients actually, they lack communication, lack of follow-up contact after they receive the treatment. It's very hard actually to collect such information. I think a much more important application of those AI models actually is to really identify patients that have a higher risk, of developing relapse, recurrence following specific treatment. I also identify which patient may be better off, receiving this treatment option compared with the other alternative treatment option. So those would be much more valuable and much more important for the patient to benefit the patient treatment care. Yeah.
Thank you.
Hi, Professor. Thank you very much. It's a very nice presentation. Just I have a one very, you can say silly questions. Silly question is actually how you label the data. So I assume that you in your group you have a physician, right? Physician or doctor who actually help to label your data. Because 1 year ago I tried to do some research with the bronchitis, but then I had to stop because I don't have the label data. Because we can download the data from Kaggle, but it is very hard to how to do this labeling. So the data set you are using, it is already labeled, so far I could understand.
Yeah, there are two different types of data we have. One is the TCGA. TCGA is one of the most comprehensive, high quality, reliable, multi-omic data together with histopathological image public database. So it's, I think it incorporates 33 different types of cancers. So basically covering all the major solid tumors. So it really depends on the type of cancer. Some data may be very limited still. The size of data may be very limited, but for lung cancer, they're very substantial, very large scale. So that's one data type. The other is like in-house collected data. We collaborate with different groups from different hospitals. So yeah.
So is this data is accessible publicly?
The TCG is accessible. Okay. You can download them. Okay. So high quality annotation, even including the omics data, not just the the histopathological images, but
And
also the
Professor,
sequence.
Professor, I want to know one thing. For which data set is not labeled, did you apply any automatic labeling or all the manual labeling? So what kind of labeling technique you used for the non-labeled data?
Labeling technique.
Yes.
That's a very good question. So there are many data augmentation strategies you could potentially utilize. Some approaches, previous ones, they like the one I mentioned, with tiling approach, we partition into smaller tiles. That's why it's not high quality, not reliable, to be honest, because you can mistakenly include a lot of, non-cancerous images, and you treat them, label them as cancerous. So you could make a mistake in this process. There are some weakly supervised or even self-supervised techniques available now. Yeah. I think the field is progressing extremely fast. So some groups, for example, from Harvard Medical School, they are already developing histopathological foundation models. They utilize, how many? I think they utilize more than 100,000 whole slide images, high resolution, and their generalized model, pre-trained generalized model, can be applied to address more than 30 different clinical questions, covering diagnosis, prognosis, treatment, everything. I suppose, all the major treatment outcomes they can cover now.
Thank you.
Yeah.
Thanks, Jianning. We've got a question online here. And the question is, would it be possible to translate these algorithms using radiological images instead of pathological images?
That's a very good question. So that, in my personal opinion, radiology images, the information it contains are less informative compared with the high resolution. Even can reveal the organization, spatial arrangement of single cell. I suppose of course, we can develop AI approaches that can integrate like multi-modality image data, including the CT scan, whole body CT scan, the mIHC, and also the whole slide images. So one way forward is actually to develop those multi-modality AI approach would be very powerful, very useful still. So that's one thing. Another thing I think is to couple with some other sequence data or even electronic health records data. So that will become, I reckon in Australia hospital system in the future, every patient, their EHR record will be put on the cloud server. So basically, of course, we have to ensure that patient privacy protection. But in the end, we will imagine that in the future, the foundational AI model will be able to diagnose, even perform screening at a relatively early stage, identify patients that may have relatively high risk over how many years, to come, that may develop specific type of cancer. I think that would be possible in the future. That really depends on the development of foundational models that can incorporate multiple other factors like the insanity, different, genomic background profile, and also the patient history, even the personal living style, lifestyle, I guess, hobbies, things like that. Also family inherited, genetic inherited status, things like that, I guess, yeah.
Yeah, great, thanks. Any other questions in the room? There's another one at the back here.
How do you see this research output affecting sort of like medical understanding of cancer? So if you have something like your models where you're looking at images, you can sort of look at, like, say, a saliency map and identify which parts the model actually looks at or sees as important, and how's that sort of going to enhance like the understanding of cancers?
Yeah, I think in terms of the biomarker discovery, certainly the AI model will be very powerful in terms of identify different type of biomarkers, at the image level, at the, like, for example, there are some other, combinatorial efforts that try to look at multi-omics molecular profile data, also the paired medical images, like including CT scan, including the whole slide images, and also some other type of data. For example, from the patient peripheral blood samples. There are also other blood sample derived biomarker that can be inferred or identified by those AI model. I've seen there are some other approaches, for example, for the colorectal patients, early stage diagnosis of colorectal cancer patient, they are sequencing the T cell receptor repertoire, B cell receptor repertoire, and also together with those images, you know, in the end would be like typical multi-modality data integrate together, and the AI identify different type biomarker, integrate them together to better inform, for example, potential treatment for the individualized patient. Yeah, that maybe one day it may become a reality.
There's another question online here. Let me just pull it up. The question here is, sorry, I'll read it here. It's still unclear how the image data labeling was done. Were there any specific algorithms or methods used, or were the images hand labeled, and were any data balancing methods applied to the model to take care of imbalanced prediction class issues?
Yeah, so like regarding the public database of TCGA, I suppose there are hundreds of pathologies they contribute to the annotation label of the TCGA data. So there are also other type of data available, like transcriptomics, sequence genomics data. There are many type of data available through TCGA. So, I mean, regarding the data imbalance issue, that's still a problem. Some of the data, they are underrepresented, specific type of data underrepresented. So there are other approaches. Just for example, the GAN approach, the general adversarial approach, can be coupled together with those deep learning training, model training. You could boost, generate some other synthetic image data. I use these data as like a label to better train your model. So just to, as an effort, part of an effort to overcome the data insufficiency or the data imbalance issue. Yeah.
Great, thank you. I just have one question before we start to wrap up here, and that's in the context of the overall benefits and opportunities around AI as you think about this field of research that you're involved in. We talk a lot about the opportunities for AI and automation. So as you think about all of the methodologies that you're developing here, how do you envisage that this really changes the workflow of clinical analysis, clinical treatment in the future, right? And the opportunity for AI to transform the field. What are your views on that?
Yeah, very, very good question, Joanna. I think AI can only be used as an assistive tool, not as a primary tool. It can only add some of the help on top of the expert knowledge. That's crucial. Expert decide, make the final decision. AI provides some guidance, perhaps assistive advice, insights. Still, the expert needs to make the final consensus decision regarding which one will be better, benefits better or would be the most beneficial decision. So we cannot just automatically rely on AI to that cannot be, yeah.
But often, particularly, it comes up a lot in the context of radiology, that the opportunity to accelerate the rate of analysis of images is enabled through the use of AI tools and techniques. And so the opportunity to speed up or change the workflow is often a part of the discussion with AI.
Yeah.
And so I wondered if that is also relevant in the context of these histopathology images you're looking at as well.
Yeah, I think it will definitely help free the valuable time of experts so that they can better focus on more challenging, more difficult, perhaps hard to make the decision cases. There are some patients, that's why we need to apply the mIHC image, because perhaps whole slide images cannot make a better decision for the pathologists. So the AI may be useful in terms better allowing them, free them time. So there's no need to discuss about this easy case. So you can better save your time, focus on more difficult. And in terms of enhancing the work productivity, save the time, it definitely would be very beneficial. Yeah. but in the end, still it rests, I mean, as a discretion of the experts to, final assess and
Yeah, so we still need the human in the loop.
Yes, I suppose so. Yeah, we still need to carefully monitor, ensure, it's within the safety of the human, within the reach of human. Yeah.
Well, great. Well, thank you very much. Please join me again in thanking Jianning for his excellent presentation.
Thank you so much. Thank you very much, everyone.
Thank you very much. So as we wrap up, thank you all for joining us today. We've really appreciated both our online Zoom audience as well as the audience in the room here. And it's always lovely to see new faces and new people joining this series of Monash conversations on AI and data science. So thank you all for joining us. For those of you who haven't joined one of our events before, if you're interested in learning more about the Monash Data Futures Institute, you can join our affiliation program and become a member of the Data Futures Institute. And my colleague Vijay is putting into the chat some sign-up links, and we'll also have some QR codes that will pop up on the screen. So if you're a Monash staff member or student, you can sign up with the blue QR code to become a member of our affiliation program, and we'll notify you about events such as this and encourage you to come along and join us. If you're one of our external guests today, you can also sign up to get news about the Institute, to learn more about our programs of work. And for that, you can sign up through the black QR code on the screen or use the link that's in the chat function. And we're very keen to continue the conversation. We'd love to hear more about topics of interest for all of you. We'll be very interested in your feedback on today's presentation. We'll be sending you a feedback form. We'd really value your response. We're also interested in what topics would you like to hear about in the future? As we think about AI transforming the world we live in, and it's been quite a year for AI, what are the topics you'd like to hear us talk about as we bring this Monash series of conversations through the remainder of this year and as we think about moving into next year as well? We'd really like to get your feedback on topics of interest, and perhaps one of our audience today will volunteer to come and join us and share their interesting research in one of these events moving forward. So we really appreciate this community that we've been building around our Monash Data Futures Institute. We're very grateful for speakers who are willing to donate their time and generosity to come and share their research with us. So thank you again, Jianning.
Thank you so much.
And we look forward to meeting all of you again in subsequent events. For those of you who are here with us in person, please hang around for some continuing conversations and refreshments. For those of you who have joined us online, it's a little hard for you to join us in refreshments, but maybe we'll see you in person next time. And we're really glad you were able to join us today. So thanks very much, everyone, and have a good evening.
Thank you much, everyone.